Yes, I'm Tommaso Alberti, and I'm a researcher at the National Institute for Geophysics and Vulcanology, Rome. And here are summarize some results that we obtained in the framework of scale-dependent predictability in complex systems and applications in various fields, and two more here in turbulence and paleoclimate variability. This is a joint work with a lot of colleagues. Some are here, like Davide, and Valerio was connected, and also Francois, Raif, Fabio, and Nico, and more will come probably. So these are my interests that covers the extreme weather events and impacts on different sectors like the aviations, and in particular focusing on the Euro-Mediterranean region, and also aquatic events and solar hazard. We are framework with Davide, the climate media framework, which needs to understand how these extreme events are changing in the framework of climate change, and we are developing the same analysis for aviation turbulence. And I always fascinated due to my bias given by my former supervisor Vincenzo Carboni on turbulence. So I worked a lot on different approaches for investigating energy transfer mechanisms and intermittency in fluids and plasmas. And I'm also interested in tipping points, and in particular to find something on early warning indicators. So the presentation mainly focuses on these two different things, and the idea came a few years ago with discussion with Davide and Valerio, because we have to define which is rare and which is extreme in physical system, complex system, and real-world system. And so there are different things to do this. The first one is the statistical methods that gives you a framework for determining the probability of exceeding a specific threshold, and typically this gives you some return period, and the distribution is a generalized Pareto-like distribution depending on the field that you are in. But there is an interesting method which has been developed a few years ago by Valerio Lucarini, which is based on characterizing the triggering mechanism of the extreme events, which is based on the Poincare recurrence theorem, and in particular looking at the phase space of the system. And so this is the focus of the presentation. We started here because you know very well that systems, a lot of systems possess attractors, so it's important because if we have an attractor, we can make statistical long-term projections like in the climate, but we can also make some kind of prediction, at least up to the Lyapunov time, like in the weather predictions. The formalism of the developed by Valerio a few years ago is based on looking at a specific point of the trajectory, then define a radius around this specific point, and to look at all the trajectories of the system that visit this hypersphere, sphere, or circle, depending on the dimension of the system, and to find which is the logarithmic distance, so the logarithm of the distance of the points that fall within this hypersphere. And if you look at the probability of coming back within this hypersphere or circle around the point, the Freitas-Storm modified theorem modified by Lucarini gives you again a generalized Pareto-like distribution, which depends on two key parameters. The first one is this theta, which is known as extremal index, which quantifies the clustering of extreme events around these points. If theta is close to 1, the extremes are independently. If theta is less than 1, and in particular if approached to 0, the extremes tend to cluster. And so this means that the system has some kind of memory or persistence in the dynamics, and can be seen as a measure of the resilience of the system, which is a new word that we learned in the past year. So lower values indicate the probability of loss of resilience. And the second parameter of the distribution is the local or instantaneous dimension D, which is a positively defined quantities that describe the scaling of the hitting times or the measure near the point. So this is a local measure, and it quantifies the number of the number of degrees of freedom of the system, and in particular, if you have larger, so increasing the dimension, you have more feedback or forcing mechanisms that are representative of possible critical transitions of the system. The main problem is that if you look at the Lorentz system, for example, you have that the distribution of the dimension is quite good because these are the two fixed points that are the low dimensional fixed points. The unstable regions are mainly located around the wings of the attractor, which is what expected for the trajectory of the Lorentz system. But this is globally, so these two metrics, D and theta, are global measures, so allows you to follow the dynamics over times, but not to really follow the dynamics over scales. So, since we know that real-world systems, complex systems, are made by components that interact each other and that typically evolve on different time scales, the idea that we had is to first decompose the time series over different scales and then to evaluate these metrics for the different scale-dependent reconstructions. And in this way, we obtain, again, theta and d, but in this case are not only dependent on time, but also are also dependent on the scales you are looking for the process. And this is in particular important for identify which scale-dependent process can be beyond the memory loss or feedbacks, and also to identify some critical scales for the changes in the dynamics. These are the two original papers, one which is published on chaos and was based on the deterministic and stochastic version of the Lorentz system, and the other one was on turbulence. And this is the first part of this presentation, because probably all of you know that turbulence is a really old and unsolved problem. It's fascinating scientists for centuries because we understand more or less how the energy cascade works, so how the energy is transferred from large to small scales, but we don't understand how the opposite behavior also occurs, and typically develops for this critical parameter. And this is the picture by the original picture by Leonardo da Vinci. And then there was a lot of experimental and also theoretical understanding in a phenomenological way of the turbulence. And it is the fantastic opportunity to test our formalism, because turbulence is characterized by singularities in the energy cascade mechanism, but also by dissipation and possibly some stochastic rules around the cascade, but also at the dissipation frame. And so we have a lot of scale-dependent dissipation mechanism, and this is also connected to the fact that we have some kind of extreme events, so the singularities that can dissipate the excess of energy that is injected at the large scale. We use an experimental framework, which is a von Karman experiment whose data are now provided by Bérenger du Brul in France. And this is the experimental setup, which is formed by a cylindrical tank and two coaxial and counter-rotating impellers. When you change the force that you apply to the two impellers, you can have some kind of noisy dynamics if the impeller are symmetric, or you can break these symmetries and you can generate some kind of large-scale jumps between two states of the system. And you can follow this one by using a control parameter that depends on the force that you apply at the two impellers. And what is interesting is that in both cases you have turbulence, because the medium is turbulent, but in one case, turbulence is statistically symmetric, so it seems like a noise, while in the other case, you have jumps among two states. You can see that, of course, there is an Kolmogorov-like spectrum for both cases, but if you look at the attractor, and so if you look at the phase space, the attractor is completely different. You have a confined shape for the noisy case and a two-lobe attractor, which is representative of the two states for the non-symmetric case. And when we analyze it with our framework, we know that for the symmetric case, so gamma zero, we can see that when we change the scales we are focusing on, the shape of the attractor is not changing, and also the distribution of the matrix is not changing. So this means that we have some kind of scale invariant attractor among the scales. When we look instead at the other case, so the non-symmetric scenario, when we have jump, we can see that we have some kind of forcing also at the small scales when we have some kind of circular distribution of the phase space. And when the scale increases, we can see the formation of the two lobes of attractor, which are low dimensional fixed points with respect to the high dimensional noise that is present at the short scales, but also at the unstable fixed point. So we have a bifurcation among the scales, and in this case, we have some kind of scale-dependent attractor measures. And if we follow this, not only over frequencies or over scales, but also over time, we can see that when we have some kind of large-scale jumps, we can see that there is an activation not only at the large scale, but also at the small scales. And you can see that the resilience is lost at the large scale. So combining the two, we have some kind of long-term resilience around large-scale transition at low frequency that breaks the symmetry, but the restoring of the symmetry is driven by the higher frequency. So this is a proof of the active mechanisms that are active at both low frequency and high frequency. So this is important for understanding the role of short scale, so intermittent events on the cascade. And if we average, we have that at the high frequency, the dimension is larger than the expected one, because we have a lot of active feedbacks, both on the short end, but also on the large scales through the energy cascade that moves energy towards the high frequencies, while the dynamics at the lower frequencies, low dimensional, because we have the two stable fixed points. And the second application I will show here before going to lunch is the xenogrid data. This is an interesting record over the last 66 million years to show the temperature and carbon fluctuations over the Earth's history. Previous analysis shows that there were 4 climate states, 2 warmer one and 2 cooler one. And this is the transition from warm state to the cool house in the present time, which is called ice house, because we have ice both at the North Pole and the South Pole. And if we look at our dimension and extremal index distribution, we can see, for example, that during the cool house, there is missing of activation of feedbacks at short scales, which is present in the warm period, but which is also present now in the ice house period, when we have ice sheets at the both poles. We can see that there are some jumps both in the dimension here and also reduction, loss of resilience in theta here. And this is a well-known event, which is the Paleocene thermal maximum, which was a warm event occurred 54 million years ago. Then we have some kind of activation of feedbacks also at large scales, which are the so-called Milankovitch scales, which are related to the orbital parameter variations and effects on the paleoclimate variability. And we can see that the ice house is quite similar to the warm period with respect to the cool house. And the second one is that if you look here, we have a decrease in the theta values. That means that we are most probably to lose resilience now than respect to the previous one. So it seems that now we are approaching a different kind of climate states. And if we introduce another matrix which measures the coupling between the two time series, so the oxygen and the carbon, we can see that there are some kind of joint activation during some specific tipping points that's been also identified by Rousseau et al. In 2022. But there is an increase in the coupling and in the strength of the coupling during the last years. So overall, if we look at the distribution of the dimension as the time scale increases, we can see that the ice house peaks at larger dimensions, while the cool house, so the most similar cold period, peaks at lower dimensions, while the two warm periods are peaked around the same larger values with respect to the cool house, but lower values with the present climate states. And we see also that there is a complete different shapes in terms of the resilience. We have most probably loss of resilience during the ice house, so the present period, with respect to the warm house and also the cool house. So if we summarize these results, we can see that the cool house is the most resilient state, which is dominated by lower number of feedbacks, We have then two warm periods which have medium resilience and medium number of feedbacks, while the current ice house is the most dominated by feedbacks, and the resilience properties is also the lower one with respect to the other. And just before concluding, I will focus on this warm tipping that I was mentioning before, which is the Paleocene-Eocene thermal maximum, where 56 million years ago there were larger temperature variations around 5 to 8 degrees Celsius in a few thousand years. That was triggered by a huge amount of release of carbon into the atmosphere. And you can see that we have a strong activation at almost all time scales, so there is not a specific dominant time scale for this event. We have a loss of resilience, and we have a lot of coupling, as expected, between the carbon and the oxygen cycle. Why this is important? Because this is the counterpart of the actual global warming. So it can be used as a proxy to investigate how the global warming will do. And if we focus on the ice house, so the current period, we can see that it's interesting that during the last 3 million years, we have a lot of number of feedbacks, both at the large scale, but also at the short-term time scales. We have a reduction of the resilience, and we have strong coupling, especially at the Milankovitch time scales between the oxygen and the carbon. This is expected because the last, especially the last 1.2 million years, were characterized by regular cycles among variability over 41 kilo years and 100 kilo years. And you can think that this could be an interesting thing and could be good because we have some kind of oscillatory behavior, but this is not good because we can lose resilience easily through a Hawke bifurcation with respect to the fast fluctuation that we have in the warm period. And so concluding in this framework, we can see that we cannot construct a unique model for reproducing the Earth's climate history. And in particular, we can see that tipping points occurred in a different way that depends on the scale, but depends also on the climate state we are. And in particular, we show that now the ice house is a cold period. We have ice sheet at the poles, but it is most similar in terms of dynamical properties to the warm periods with respect to the previous cold one. And in particular, we are probably losing resilience in a faster way because we have also more feedback mechanisms and stronger coupling among system components. And you see that 56 million years ago, we had a strong coupling among carbon and oxygen, but there was not anthropogenic effects. Now we have also an additional feedback, which is an external feedback. And again, you can think that a system that oscillates most regularly is good, but in this case, we can lose resilience more easily than previous ones. So short-term variability can act as really as a destabilization factor and can propagate over different time scales, how we show in the Paleocene Eocene thermal maximum. So I can stop here and thank you for the attention.
Okay, yes, please.
Okay, so I have a question. Because 56 million years ago, the geology of the Earth was different. The tectonic plates were different, which means that the ocean gyres were also different. You have different currents going on. Do you think that could be one reason why back then there was maybe fewer feedback mechanisms than currently?
Yes, indeed, it's a good question because if you see here, this one is okay, because starting from the cool house here, it was starting the ice sheet formation in the Antarctica, and then starting more or less here, we have the formation in the northern hemisphere, and this acts, of course, as in the feedback mechanism. mechanism, because the ocean feedback was changed because we have ice that can be lost into the ocean. And so this is, of course, one of the key mechanisms that can act in the present time. And yes, in this case, this is for raminifera, so we can make some similar analysis also for ocean deep circulation to see if there is a proof. But I suspect, yes, the ocean is fundamental.
So
this one.
the idea that the plate tectonics and where things were located, how it connects to the gyres, is there a way to model those sorts of effects with what you're doing? Because that wouldn't be a very good analog if that makes such a big difference.
You mean in terms of the modeling?
Yes, because the CO2 levels, I agree, are the same. You know, that's sort of those ideas. But if they're highly impacted based on where those ocean currents are located because of the plate tectonics, is there a way to sort of model how those gyres would change with plate tectonics and overlap it with what you're looking at?
Sure. I don't know if there are some model of this, but the main.
No, I mean, in principle, the answer is yes. The question is whether it's a good model.
Yeah,
sure.
Because this is the main finding. So you cannot have a unique interconnected model among the fields. So you have to focus on shorter periods that maybe for the geological one are good, but you have to focus specifically on that. But yes.